Welcome to the next video in the Introduction to Chemistry 11 series. In this video, we will talk about nomenclature, specifically ionic and covalent nomenclature, using the IUPAC method. IUPAC means the International Union of Pure and Applied Chemistry and is the standard bearer for how to name things in chemistry. We need to start with the periodic table of the elements. With any standard periodic table of the elements, every box on the table will have 3 or 4 pieces of information right off the bat. The atomic number, the atomic symbol, the atomic name, and the atomic mass. Now, the atomic number is simply the number of protons in the nucleus of any element. If it is a neutral atom, it is also the number of electrons in the electron shells. The atomic symbol is either a 1 or 2-letter set of symbols to identify each element on the periodic table. If it is only 1 letter, that letter is capitalized always. If it's 2 letters, the first letter is capitalized, the second letter is always lowercase. For instance, oxygen, capital O. Aluminum, capital A, lowercase l. Hopefully on every periodic table you see, it will have the atomic name. So in the example I've given here, I've got the atomic number of silicon is 14, the symbol is capital S, lowercase I, and the name silicon. The fourth piece of information that's very important when we're doing calculations is the atomic mass. The atomic mass is recorded in atomic mass units, and on standard periodic tables, it will be a weighted average of all the known isotopes of that particular element. If we refer back to a standard periodic table, there's often a solid line that separates boron, aluminum, silicon, germanium, arsenic, antimony, and tellurium. On my table, I've drawn this in green. This separates the metals from the nonmetals. The metals are found below and to the left of what we call the staircase, and the nonmetals I've shown in red to the right and above the staircase. Metals in general are known to be malleable, ductile, conductive of heat and electricity. They all have a bit of a shine or a luster to them. When they form ions, they form positive ions. When reacting with oxygen, they form basic oxides. And in most cases, they have high melting points, boiling points, and density. And almost all of them, with the exception of gold and copper and a couple of others, are silvery in color. Our nonmetals, to the right and above the staircase that I've shown in red here, tend to basically have the opposite properties of metals. The properties of metals are malleable and ductile. The property of nonmetals are brittle, poor conductors of heat and electricity. They tend to lack luster, so they are dull. When they form ions, they form negatively charged ions. And when they react with oxygen to form oxides and dissolve those oxides in water, they all form acidic oxides. Generally speaking, the nonmetals are going to have low melting points and boiling points, low density as compared to the metals, and they have a wide variety of colors. Oxygen is slightly blue, chlorine yellow, bromine can be blood red, iodine is purple, and so on. Between the metals and the nonmetals, those elements touching the staircase, specifically boron, silicon, germanium, arsenic, antimony, and tellurium, go by a new name, and that's the metalloids. The metalloids are transitional metals between the metals and the nonmetals, and so have a blend of properties. The metalloids look like metals, but they behave like nonmetals. Some of them are brittle, but some of them are malleable. In all cases, these are semiconductors. They are less conductive than metals, but more conductive than nonmetals. Some are dull, some are shiny, and a few of them can form both positive or negative ions depending on the chemical context. In other chemical contexts, they can form covalent bonds instead of forming ions. Now that we know how to describe the elements on the periodic table, now we'll combine them into compounds. Generally, there are three kinds of compounds that IUPAC is concerned with: covalent compounds, ionic compounds, and organic compounds. First, covalent compounds. These occur when the bonding electrons are shared between two nuclei, and they typically occur between two nonmetals. That's a good basic way of understanding it, but in truth, a covalent bond happens when the difference in electronegativity between the two elements that form the bond is very low. Low electronegativity difference between the two elements gives a covalent bond. The second kind of bonding is called ionic bonding. In this case, electrons are transferred between atoms and form ions. The metal loses an electron or two or three. That electron is transferred to the nonmetal, and so the metal forms a positive ion, the nonmetal forms a negative ion, and then those positive and negative ions are electrostatically attracted. Now, what I've just described is what happens with a simple ion. But ions can be simple or polyatomic. They can be positively charged cations or negatively charged anions. And a general rule of thumb is ionic bonding happens between a metal and a nonmetal or a polyatomic ion. Once we've established when covalent bonding and ionic bonding takes place, next we can describe how to name them. There is a third kind of bonding, organic compounds, but that has a completely different naming system, and I will deal with that in a different video. First, covalent nomenclature. We can think of it as bonding between two nonmetals of similar electronegativity. In this case, we're going to name the most metallic element first, that is the element closest to the staircase, and we're not going to change the name at all. If there's more than one of these elements in the compound, we will need to use the Greek prefixes to say how many of those elements are present. As our understanding gets better, we realize the most metallic element is actually the one with the lowest electronegativity, but we'll deal with that later. In covalent bonding, the least metallic element is written last, and we change the ending to IDE, that is ide. That element will always have a prefix to indicate the number of elements in the compound. For the most metallic element, we do not use a prefix if there's only one. For the least metallic element, we always use a prefix, and those prefixes are based on the Greek stems. The Greek stems, very simply, one means mono, di indicates two elements, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, deca 10, and we can keep going. There are Greek stems all the way up into the hundreds, but if you know the 1 through 10, mono through deca, you will be able to name almost all of the covalently bonded compounds you will see. Let's look at some examples. SO3, sulfur and oxygen. Sulfur is the most metallic because it is closer to the staircase. Oxygen is the least metallic, and so we change the ending to IDE. There is one sulfur and 3 oxygens, so my prefixes, nothing on the sulfur, tri on the oxide, sulfur trioxide. Second example, P2O5, phosphorus is the most metallic, oxygen becomes oxide as the least metallic. 2 phosphoruses and 5 oxygens mean diphosphorus pentoxide. Third example, CS, carbon and sulfur. In this case, carbon is the most metallic and is written first. In this case, sulfur is the least metallic and written second with the ide ending, and there's only one of them, so we call it carbon monosulfide. The second kind of bonding is ionic bonding, which takes place between either a metal and a nonmetal of significantly different electronegativities, or between a metal and a polyatomic ion. If we have ionic bonding, we name the most metallic, or the metal, ion first. Sometimes it's a metal ion, sometimes it's a positively charged polyatomic ion. In any case, it's the cation. The cation is always named first, and if it is monovalent, has only one possible positive charge, then we simply use the name off the periodic table, nothing else. If the metal, however, is multivalent, which does apply to almost all the transition metals and the poor metals, then the charge on that metal ion must be indicated using Roman numerals. Second, we name the non-metal or negatively charged ion the anion. If it is a simple ion, that is a single atom with a charge, then we change the ending of that to IDE or ide. In our first example, we use a monovalent metal ion, that is an ion that only possesses one possible positive charge, potassium, and the simple anion, sulfur with a -2 charge, or sulfide. The name then becomes potassium sulfide. In our second example, again a monovalent metal ion, calcium, a simple anion, bromine, which becomes bromide, so the name is calcium bromide. In our third example, we use multivalent metal ions, in this case iron, and it is an iron 3+ charge. So when we name it, we say iron Roman numeral 3, and then the oxygen becomes oxide, so iron 3 oxide. Our fourth example, we use the multivalent metal ion copper, in this case it's a copper 2+, and we put it together with chlorine in the form of the chloride ion, so it becomes copper 2 chloride. Those 4 examples dealt with simple ions. Next, we'll deal with polyatomic ions. Since poly simply means many, a polyatomic ion refers to an ion formed from many atoms bonded together. The definition of a polyatomic ion is a group of at least 2 atoms covalently bonded together, carrying a net charge and acting as a single particle. Most polyatomic ions are anions, that is, negatively charged ions, and contain oxygen, although there are a few positively charged cations and a few anions that do not contain oxygen. By far the most common ending for a polyatomic anion is ate, A-T-E. That refers to the polyatomic ion with the most stable oxidation state, although other states are possible and may even be common. Let's deal with the positively charged polyatomic ions first. There aren't very many. Remember, a polyatomic cation is multiple atoms covalently bonded together, acting as a single particle, and this time carrying a net positive charge. There really are only 2 commonly used polyatomic cations: ammonium, NH4 with a 1+, and hydronium, H3O with a 1+, used in acid-base chemistry. There are several other unusual polyatomic cations, such as phosphonium, fluoronium, and the mercury 1, which is actually 2 mercury atoms bonded together with a net 2+ charge. But those are quite rare. Far more common are the polyatomic anions, the negatively charged ions. Once again, this is a group of atoms covalently bonded together, acting as a single particle and carrying a net negative charge. There are literally thousands of polyatomic anions, and most of them are oxyanions, that is, anions which contain oxygen. The oxyanions in their most common oxidation state will carry an ATE or an ate ending. If they're in a lower oxidation state, that is, fewer oxygens, they then have an ITE ending. Some of the most common ates include nitrate, sulfate, phosphate, and the halogens chlorate, bromate, and iodate. In almost all cases, if you remove one oxygen but keep the same charge, the ending simply changes to ite: nitrite, sulfite, phosphite, chlorite, bromite, and iodite. The most commonly used oxyanions I call the big four. The big four are nitrate, NO3 with a -1, carbonate, CO3 with a -2, sulfate, SO4 with a -2, and phosphate, PO4 with a -3. When combined to make compounds, the big four act as if they were simple ions. Nitrate with lithium becomes lithium nitrate, carbonate with sodium becomes sodium carbonate, calcium with sulfate, simply calcium sulfate, and magnesium with phosphate, magnesium phosphate. Other very common oxyanions include acetate, chlorate, bromate, iodate, oxalate, borate, arsenate, and silicate. A calcium chlorate would have a formula of Ca and then brackets ClO3 bracket 2 to indicate it takes 2 chlorates to balance the charge on the calcium 2+ ion. Similarly, an aluminum oxalate would have a formula of Al2 and then a bracket C2O4 bracket 3 to indicate I need 2 aluminum ions and 3 oxalate ions to add up to 0. When dealing with oxyanions, there are a few very simple rules that help us determine the names of many, many anions. Start with the most common oxidation state, 8. If you add one more oxygen to that structure, keeping the same charge, we indicate this with the prefix per, a per8, such as perbromate. If you remove just one oxygen and keep the charge the same, the ending changes from an 8 to an ite. So we now have BrO4-1 is perbromate, BrO3-1, bromate, BrO2-1, bromite, and if possible, and we can remove one more oxygen, BrO with a -1 becomes hypobromite. The prefix per indicates one more oxygen than 8, ite indicates one less oxygen than 8, and hypo-ite indicates 2 less oxygens than the 8. So potassium perbromate would become KBrO4, ammonium bromate, NH4BrO3, lithium bromite becomes LiBrO2, and calcium hypobromite becomes Ca bracket BrO bracket 2. There are a few polyatomic anions with an ending of IDE that would normally suggest a simple ion, but are in fact polyatomics. These include hydroxide, the basic ion, cyanide, Cn-1, and peroxide, O2, 2-. When building compounds, again, we treat them like any other anion. Aluminum hydroxide would then be Al bracket OH bracket 3, and magnesium cyanide would become Mg bracket Cn bracket 2. The next family of polyatomic anions are those which contain hydrogen, specifically those that started with a -2 charge and then one hydrogen was added, resulting in an HX-1 ion. To those ions, we add the prefix bi. So carbonate, which started with a -2 charge, becomes bicarbonate, HCO3-1. Sulfate, also a -2, becomes bisulfate. Sulfite, bisulfite. The one anomaly is oxalate. When you put one hydrogen with oxalate, it becomes binoxalate. The compounds formed then become barium bicarbonate, BaHCO3, all in brackets with a 2 outside. An iron 3 bisulfite would be Fe bracket HSO3 with a bracket 3. And finally, with binoxalate, ammonium binoxalate would be NH4+, HC2O4. Note that the hydrogens are kept separate. This concludes our lesson on covalent and ionic nomenclature using the IUPAC naming system. Please subscribe to Chemist Corner, like, comment, and tell all your friends.